All right, guys. So we're going to continue our section in probability here. And we're going to start out of section 10D in that red book. That's on page 250. So if you're following along in the book, that's perfectly fine. If you just want to follow along with the notes, that is perfectly fine. I just want you all to have accessible where I'm pulling these examples from. So the first section we're going to look at today is theoretical probability. Now, theoretical probability is just the chances that something could happen in theory. We're not actually doing any kind of experimentation, like where I had you all roll the dice last class. Today we're just talking in theory, what are the chances? So the way that you calculate that, if a sample space has n outcomes, or n is just a number here, which are equally likely to occur, each outcome has the probability of 1 over n of occurring. So for example, if you think about a dice roll, a dice has 6 outcomes that can occur, and it has a 1/6 chance of getting a 1, of getting a 2, of getting a 3, a 4, a 5, and a 6. And so the formal definition of the probability of event A, we read this as probability of A, or P of A, is you do the number of outcomes corresponding to A divided by the number of outcomes in the sample space. So we're going to practice this principle of theoretical probability on a couple of examples to start here. So we're going to start with example 6 here from the book, page 251. So let's suppose we got some tickets selected from a basket, and in those we have 3 green, 4 yellow, 5 blue tickets, and we want to determine the probability of the following. Getting a green ticket. So we'd say, okay, how many greens are in there? There's a total of 3, and then out of how many? Let's see, 3 plus 4 plus 5, that is going to be our denominator here. So 12 total. So we've got, that would be 3 out of 12, and we can go ahead and just reduce that fraction to 1/4. So when you're listing these probabilities, again, you can always list them as a fraction, you can list them as a percentage, you can list them as a decimal. I will always write the fraction because the fraction is where you get the other ones from. So if you're asking yourself, which one should I put here? I would always put the fraction. If you prefer to put something else, that's perfectly fine. So we got now green or yellow. So our two options here are that we can pull a green ticket or a yellow ticket. So that gives us, in theory, 7 tickets. So there's 7 green or yellow tickets out of 12, and that is not going to reduce. Let's see here. Getting an orange ticket. Well, we've got green, we've got yellow, and we've got 5 blue tickets. There are no orange tickets to be found. There's 0 orange out of 12 total, which is 0 divided by 12 is just 0. And then lastly, we've got every possible combination here. We've got green, blue, or yellow. That gives us a total of 12 tickets out of 12, which can be simplified to 1. So obviously 0 represents a no probability chance of occurring, and a 1 represents a 100% chance of occurring. And so when you're writing these things out, it's important to note that this 1 represents 100% and that the 0 represents 0%. So then let's go ahead and look at another example here. So in this next example here, we're going to use a 2D grid to start showing our sample space. So a 2D grid is just a different way to illustrate that. So the thing that we're going to illustrate is tossing a coin and rolling a dice. So the sample space for that, you really just have to make 2 axes here. So I'm going to make the x-axis here the dice, and I'm going to make the y-axis here the coin. And so options for a dice are 1, 2, 3, 4, 5, or 6. And our options here for a coin are heads or tails. And this is just one way that you can represent these different sample spaces. You can use a tree diagram. You could physically write them all out yourself. It is up to you. But each of these points is going to represent an outcome in this sample space. It's just another way to easily show it. So we got the probability of tossing a head. Now we need to remember this is out of our sample space, not just a regular coin. So the amount of outcomes that involve getting a head are 1, 2, 3, 4, 5, 6 outcomes out of a possible 12. And we're going to go ahead and reduce that fraction there. 6 out of 12, you can take a 6 out of both to reduce that to 1/2. So then we look at, okay, the probability of getting a tail and rolling a 5. So tail and rolling a 5, the only outcome that's going to work there is literally just getting a tail and getting a 5. So the outcome, or the probability of that would be 1 outcome out of 12 possible outcomes. And then if you look at tossing a tail or rolling a 5, we have to, so or implies a bigger choice of things than and does. Because and means both things have to be true. Or means one of those things has to be true. So if we're looking here at the 2D grid, the ones that are rolling a 5 are this one and this one. You can get heads in 5 and tails in 5. But also, we're counting all of the ones for tails. So we have to include tails 1, tails 2, tails 3, tails 4, and tails 5. So in total, we are counting 7 outcomes there for that for this probability. So we would say, okay, well, our denominator is still going to be the same, but this time our numerator is going to be 7 out of 12. And so there are multiple ways to illustrate these probabilities. You can use a tree diagram, you can use a 2D grid. We're going to look at another example where they use a Venn diagram to do so. And it's important for you all to see it in different ways so that you can communicate this information in different ways to people. So that, and when you see it, if someone puts it a different way, that you are readily available to understand the way that it's going. So this is example 10. And the way that this is set up, we've got a Venn diagram here. B stands for blue eyes. So anybody who is in this circle is identified as somebody of having blue eyes. And everyone outside, but still included in the universal set here, are people who do not have blue eyes. And so if we want to do the probability here of having blue eyes, that would be everybody in this Venn diagram right here. So 3, 6, 8 people. So 8 blue eyes out of the total here. So we'd have to combine these two to get that denominator. So that's 8, and here is 12, 15. So that would be 23 total that have blue eyes. And so if we're doing the probability of them not having blue eyes, there's a couple of ways to think about this, to do this. The first, the most simple way is you could just count these and be like, okay, 1, 2, 3, that's going to give me 15 out of 23. So 15 that have not blue eyes out of the total. And typically, with those complements, these are considered complements of each other because you either have blue eyes or you do not have blue eyes. The complements, if you add them up together, should add up to a full 100%. So if you do 15 23rds plus 8 23rds, they add to 1 or 100%. Because if you combine these fractions right here, you would get 23 out of 23, which is the full 100%. And so we're going to look at just another example for theoretical probability, and then we'll be wrapped up on theoretical probability for the day. So we're going out of example 11 here. So we've got a class of 30 students. And in that class of 30 students, 19 study physics, 17 of those study chemistry, and 15 of those study both. And so what we've got to do here, first off, is with that information, we have to, if we're going to perform some sort of probability calculations for this, we have got to create a diagram for us to understand that. So a Venn diagram is another way to do so. So if we've got this Venn diagram here, and we're going to say that this circle is going to be the people that study physics. These people are going to be the people that study chemistry. We've got the universal set here because there may be some people who study neither. And we're going to start with the information that we know for certain. And that information that we do know is that 15 people study both physics and chemistry. So in the middle of that Venn diagram, I'm going to put 15. And we also know that 19 of those people study physics. So if we have 19 that study physics and 15 of those study chemistry as well, the people who exclusively study physics, we're going to do that 19 right there minus 15 to put a 4. Those are the people that exclusively study physics there. So then we're going to do the same thing for chemistry here. So we've got 17 who study chemistry and 15 study both. So we have to say, okay, well, how many people would exclusively study chemistry? And that would be 2. From there, we have to figure out, okay, there's some people in this class who are not science people. They take neither physics nor chemistry. What amount of people is that? So we'd say, okay, well, 4 study physics. And if we add that to the people who study both, so physics, both, plus the people who study chemistry, plus whatever the amount of people we're missing here is, the entire class here is 30. So then let's see, 4 and 15 is 19. 19 and 2 is 21. So 21 plus that is going to give us 30. So that's a total of 9 people. So we now have a Venn diagram that accurately represents this situation. And so now we can readily do some probability here. So we're going to use this Venn diagram to calculate the probability that a randomly selected student, first off, studies both things. So we have to think, okay, how many people studied both? That's going to be 15 out of the total here, which was 30. And we can always reduce that. 15 out of 30 reduces to 1/2. So then we look at studies at least one subject. So at least one subject, we've got to include the people that study physics, which is 4. We have to include the people who study both because it's at least 1. So the people that study both is 15. We also have to include the people that study chemistry solo. So plus 2, and that's still going to be out of 30. So let's see, 4 plus 15 is 19, plus 2 is 21. That's going to be 21 out of 30. If you take a 3 out of both of these numbers right here, that's going to give you 7 out of 10. So guys, if you want to, you can pause it here and you can try to attempt these last 3 on your own. you're more than welcome to do that. I'm going to go ahead and finish these 3 out. So the probability here that somebody studies physics but not chemistry here, so that would mean exclusively physics, would be there's 4 people total out of 30. And we can reduce that by taking a 2 out of both of these things here to get 2 out of 15. So then we're looking, we say, okay, well, what if they're studying exactly one of the subjects of physics or chemistry? So we do almost the exact same thing, except now we're going to include chemistry in that numerator, which is going to give us 6 out of 30. And if you take a 6 out of both of these things, they're both divisible by 6. That reduces to 1/5. And as a good habit to get into, I would always reduce, always reduce those fractions. And then lastly, the probability that they study neither subject would be the amount of people we decided that studied neither was 9. So we're going to say 9 that study neither out of 30. And we ask ourselves, what are both of those things divisible by? Both divisible by 3. And that represents that probability. So that is our wrap up on theoretical probability. So I want you all to go ahead. If you finish this up, I do have a little investigation I want you all to do before the notes on the addition law of probability. We're actually going to figure out what the addition law of probability is. So please go to that next.